So this part is supposed to go over complex numbers, this chapter, right? This chapter is complex numbers. So we're going to start with 5-1. 5-1 has a circuit drawn like the following. Where we have a resistor R, and an inductor L, positive, negative, the voltage V of R, and our voltage V of L are represented by the following equations. VR is equal to 1 at an angle of 0 degrees, and VL is equal to 1 at an angle of 90 degrees, right? So if we were to draw this, right, we would have something that looks like the following. So at 0 degrees, we have the vector VR, right? This is VR because it's at 0 degrees. And then we have VL. VL, which is 1 at an angle of 90 degrees, right? So this is how we would represent this in graphical form. Now this says write VR and VL in rectangular form. So this would require us to, this is the imaginary part, and this is the real part. So we would then have to convert this from rectangular form from polar form to rectangular form. And this is done pretty easy if we're given angles like this, right? So we know that this VR vector is only contained on the real axis, so there's no imaginary component at all. So we can represent VR as 1 plus 0j. Make sense? Because there is no imaginary part. Yeah. Right here? Is this what you're talking about? That one? Yeah, that's VR. And that's VR up here. Yeah, this is VL. And this is VL. So VL now, what do you think VL is going to be? 0 plus 1j, because it only contains a real component. So now if we want V, which is equal to VR plus VL, what do you think we're doing? We're going to add the real components of each and the imaginary components of each. So we're going to add these two values and these two values to give us what? 1 plus 1j. Exactly. So that's part A. Part A just asks to write VR and VL in rectangular form, which we did for this part. Which we did right here. And then it says write V in both rectangular and polar form. Well, we have it right now in rectangular form. Now we got to convert it to polar form. So how do we convert V, which equals 1 plus 1j, in rectangular form into polar form? Yes. Exactly. So exactly. Yeah. So for our magnitude is just equal to the square root of 1 squared, our real portion, plus our imaginary portion, which is still 1 squared. So this is equal to the square root of 2. And this is our magnitude. Our angle, theta, is equal to the inverse tangent of our imaginary part over our real. So this is equal to the inverse tangent of 1 over 1, which is going to be equal to 45 degrees.
So you get so V with the lines is the magnitude.
Is the magnitude, yes.
You get magnitude by square rooting. You gotta take the real and the imaginary and square it, and then
Yup.
put it under the square root symbol.
Yup. You take both those values squared. So the magnitude is equal to the real, which is 1, the real component squared, plus the imaginary component squared. So just a generic way of writing it will look like this. Is equal to the square root of the real squared plus the imaginary squared. And that's your magnitude. Yup. And your theta, or your angle, is equal to the inverse tangent.
I know I can do this all. Because what I did was well, first of all, my calculator was
Radians.
Yeah, so I had all that stuff in the door.
That's all right, though. That's all right.
It was I had V.
The magnitude?
Yeah, when I didn't get the magnitude, and I didn't use 810 theta, so I couldn't have got the right form.
You might not have, but if you got something right, this is pretty much the same thing as the vectors, at least from converting from rectangular to polar.
Right.
It's pretty similar. But just remember, if you want to get magnitude from your if you're converting from rectangular to polar, polar always has a magnitude and an angle, right? So in order to find that magnitude, you got to take the square root of the real portion squared plus the imaginary portion squared.
Right.
And that's going to give you the magnitude.
And you plug that in and you get the actual magnitude.
Exactly. And your angle is just the inverse tangent of the imaginary part over the real part. All right, and so that was 5-1. It looks like 5-5 and 5-4 are similar, but 5-5 has a little more difficult numbers. So I'm going to go with 5-5 and just repeat the process for 5-4. So once again, we're given another circuit, right? Where we're given R. Oh, this is an inductor, it's a capacitor. Let's see, plus minus VR, plus minus VC, and we're given VR. VR is equal to 9.5 at an angle of 18.44 degrees. VC is equal to 3.16 at an angle of minus 71.56.
Does it matter since it's C instead of L, or I do the same method?
No, it doesn't. You do the same method. VC and VL, if it's in that form, that means it's in polar form. This is just saying, VC is just saying volts. All of these values are in volts. Right? So that's just the voltage across the resistor. VC is the voltage across the capacitor.
So now I would do 9.5 cos 18.44.
To convert, that's what part A is saying. Part A is saying convert from polar form, which is what this form is, and we want to go from polar form to rectangular. So to go to rectangular form, VR is equal to the magnitude, this 9.5 times the cosine of 18.44 plus 9.5 sine of 18.44 times all of that by j. So this is equal to 9 plus 3j.
That's after calculating.
Now, exactly, I'll do VC on the next page. VC is equal to 3.16 times the cosine of, let's go back to see what the angle is. No, it's different. VC is different. The magnitude is 3.16 for this one, and the angle is minus 71. So we just throw in that minus 71.56 plus j times 3.16 times the sine of minus 71.56. This gives us 1 minus 3j. And VC, or VR, just so I have it on this page, is equal to 9 plus 3j.
So that means 9 I hat plus 3j.
J hat.
1 j hat, 1 I hat plus minus 3j hat. So
I think I'm following.
I hats together.
Yeah, you add your real, well, it's different now. Instead of I hat, it's real, and instead of J hat, it's imaginary. But you could, but if that's how you remember it, it's identical.
Same with the vector.
Yeah, exactly. So now for part B, we have V equal to VR plus VC, right? So this is just equal to 1 minus 3j plus 9 plus 3j. The reason why I wrote it like this was just to show you that we add up our real, we add up our imaginary. So this formula right there is V, this is VC, right? This one right here is VR. So when we add up the real part, we get what? We get V equal to 10.
6 plus 6. Wait, is it plus or minus? So it makes it minus 6.
No. We have a negative 3j plus a positive 3j. 0j. Plus 0j. And then it also asks us to find the polar form of this. Well, this is easy now, right? Because there's no imaginary component, so it looks like this, right? It looks like all of it along the real axis, correct? So our angle is what? Our angle equals 0, and our magnitude of V equals what?
Magnitude is real squared plus imaginary squared. So it would be real is 10 squared,
Square root of 10 squared plus 0 squared,
which is basically I.
the square root of 10 squared, which equals 10, right? So this is just equal to, V is just equal to 10 at an angle of 0 degrees. That's part B. Part C then asks for the real and imaginary parts. Well, we know what the real and imaginary parts are because we had it in rectangular form, right? So the rectangular form of V was 10 plus 0j. So this is the real part. This is the imaginary part, right? So real is equal to 10. Imaginary is equal to 0 times j, which equals 0.
And I spent all this time on this.
But now you get it. You get it now. 420. Yeah, 423.
This is all going to be on the.
This isn't going to be on this exam.
No, teach me how to find this on like the website.
Oh, on Blackboard? Hold up. Let me yeah, go grab it. Go grab your laptop if you have it. All right, let's go over the last one I want to go over is 512.
for that change? The parallel, or can you replace the L with
Does the formula change? Say that again.
Yes, you remember how I showed you the formula in the book was CR times CL over CR plus CL?
Okay, the impedances. You're actually trying to do circuit analysis. So I would say for 512, just use the equations that they provide you with.
That is the one they provided.
So for this, for parallel, so you have current now, right? So your current is just equal to the current across the capacitor plus the current across the resistor now. Your total current in the system is equal to the two loops of current. When I draw this,
So it's right here,
yeah,
but I don't see it.
you don't see the videos?
And I go all the way here. I
Go to content, yeah,
Recitation. Bang.
go back. Go up, go up, keep going. Lectures and recitation recordings. Right
Recitation
there.
1, 2, 3,
Three.
4. Oh, okay.
Yep,
All right.
no problem. Okay, so we're given this, right? We're given IC and IR. So the current across the resistor and the current across the capacitor. This is the total current. So we could think of, and they provide us with IR and IC, right? So the total I then is just equal to IR plus IC. That's the total current in the system.
What happened to that?
To that formula of Z equals, well, they're probably trying to solve it in terms of voltage. So where you find your voltage V equals IR, right? Where Z is your impedance or resistance, which is your R. And so they might give you the current and try to find the voltage that way. But here we're just given the equations. So there's no need to solve for current using impedance, right?
Well, I have this open up right here, and it's impedance of R and L connected in parallel, and it gives you
Oh, this is total impedance, right?
right, but you have to find that.
But we're not trying to find impedance for this problem. This problem we're just trying to find current. Right?
Are we?
That's what 512 is saying. 512 is saying just write IC and IR in rectangular form, find I and find the real and imaginary parts.
Am I making work too hard for myself?
You are right now. You are. But which problem is it 512?
Yeah.
This.
I'll show you one.
Alright, let me pause this real quick. It's just going to be IR, the currents of IR and IC. So they give you the two currents. They tell you IR is 0.929 at an angle of minus 21.8 degrees, and IC is 0.37 at an angle of 68.2 degrees, right? So we want to just convert, part A says convert from rectangular or from polar to rectangular. We know how to do that. Our magnitude times the cosine of the angle. So IR is equal to 0.929 times the cosine of minus 21.8 plus J times the sine. Oh, I'm sorry. Exactly. J of 0.929 times the sine of negative 21.8. This gives us 0.863 minus J times 0.345. Now IC, we do the same exact thing. 0.37 times the cosine of 68.2 plus J times 0.37 times the sine of 68.2. This gives us 0.137 plus J times 0.344. 0.137. I'm not 100% right. I'm not 100% sure. That's what the solutions have. Sometimes these solutions are a little wrong. Let's see, 0.37 times the cosine of 68.2. That's what I'm getting. I'm getting 0.137. Are you in radians? Yeah. Yeah, your calculator may have been in radians. Okay, now that's part A. Part C, or part B, just says, yeah, part B is just equal to IC plus IR. So all we're doing is taking our rectangular form. Since it's easier to add in rectangular form, we're just going to have IC, which is 0.137, plus, what is it, 0.344J, plus IR, this is IC, and IR is 0.863 minus J times 0.344, and this is IR. So the imaginary parts cancel, and we're just left with a real part, which is just 1. So this is equal, yeah, to just 1 plus 0J. So this would once again be a vector or a complex number only on the real portion. So our magnitude is just equal to the magnitude of the real component, which is 1, at an angle of 0. 1, our angle is equal to 0. Exactly. So, and then part C just asks for the real and imaginary parts. Real, we know what the real is. It's right here. Real is 1. And the imaginary part is 0. No, you could literally just write it out as 1. But if you're going to do that, I would say write it in polar form so that you have it as just I is equal to 1 at an angle of 0 degrees.
So what was the point of them telling us it was in parallel if we weren't using that?
The circuit itself is a parallel circuit,
Right.
but we're only solving for current. So the current in a parallel circuit is just the addition of those two currents added together.
But then what's the current in the series circuit?
The current in series in it is just one. There's only one current. Because if you have just a random current, let's say if we just have a random circuit, right, with a resistor and capacitor and an inductor, all of these components are in series, right? But the current going through this is all the same. It's the same current. So this would be a voltage representation. If it gave you this as a current source, I, then this whole system is just I. So unless you add another component, which is a resistor right there, now you're going to say we'll call that I1, and we'll call this I2, right? So I is just the combination of those two added together.
Okay.
All right. You were using impedance, which didn't even come into play in the question, but
Like the example it's talking about for the one in series was impedance. So
yeah,
and it was also in parallel.
those were impedance. Okay, so I could go through that real quick. So they're pretty much trying to. We have a resistor. Let's just say we have a capacitor capacitor, a resistor, and we have some source, right? Each one of these, we could re-represent this as impedance blocks, right? So that's an impedance, this is an impedance, and this is just our voltage source. So this would be ZC, and this is ZR. So our total Z, so that we can redraw this as an equivalent impedance, as just one impedance, Z is equal to ZC plus ZR. So this is in series, right? But if we wanted to go in parallel, hold up real quick. So that we had another voltage source, right? A resistor, a capacitor. Actually, forget that resistor. And we had a inductor, and then we had a resistor, right? We could re-represent this once again as impedance blocks.
Let's say you didn't have the inductor there, though.
All right, let's get rid of the inductor. It doesn't matter. They all contain impedance, right? So this...
The equation is ZC plus ZR times ZL over ZR plus ZL. But if you don't have a ZL, it's 0 is a problem.
Well, that's not true. I'll explain why. So ZC, ZR. If we don't have an impedance, right, the total impedance, so that we have another equation that just has one impedance, we call it Z, right? We want to reduce, essentially what we want to do is reduce this impedance to one impedance. So if we do that, then Z is just actually 1 over Z is equal to 1 over ZC plus 1 over ZR. Now if we wanted to find ZC, what would you do? You would multiply this so that it looks as 1 over Z is equal to ZR plus ZC over ZC times ZR, right? Combining fractions, so that Z is just equal to ZC times ZR over ZR plus ZC. So that would be your total. When you add, it's similar, yeah. So, but remember that your ZR will only contain real components. Your capacitor, your impedance across your capacitor, and your impedance across your inductor are complex numbers. Impedance, inductors complex, and resistors real.